Okay, welcome to the lecture for Friday, April 4th. I first want to give a reminder that test 3 will be Tuesday, April 8th from 7:30 to 9 o'clock p.m. And our section is in Williams 2215. And the material covered will be chapters 11 through 16. So we finished chapter 16 on Wednesday's lecture. So today's lecture I will do a review problem from chapter 16, but then we'll cover some new material that won't be on test 3 but will appear on the final. So let's first do an example. Okay. So let's suppose we have a train. So there'll be two situations. So let me just draw the picture. I have a train moving with 40 meters per second, and then I'll have a car going at 30 meters per second, and then there's a little whistle. There's a little whistle on the train that's producing some sound, and we know that the whistle on the train has pitch 1000 hertz when just blown stationary in the air. And the question is, what do the drivers, the passengers in the car hear? What pitch is heard by the car passengers? Okay. All right. And we'll take the speed of sound to be 340 meters per second. Now, this is a Doppler effect problem. So the formula is that the frequency heard by the observer, so this guy is the observer, and this is what we'll call the source, is the frequency of the actual sound producing thing, the whistle, which is 1000 hertz, times v, the speed of sound, plus VO, and v minus Vs. Okay? So the O stands for observer, S stands for the source. Okay, now remember there are some things we have to remember about the sign convention. So let's first do the observer. The observer is, here's the source, here's the observer. The observer is moving away from the source. And so therefore, because it moves away, it gets a negative sign. So it's a negative 30 meters per second. Now how about the source? The source is moving towards the observer, so that gets a positive 40 meters per second. If either one moves towards the other, then it gets a positive. If it moves away, it gets a negative. Okay? So we'll just plug that in. We have f prime is equal to 1000 hertz is the original, and then the speed of sound is 340, plus the observer speed, or I should call it the velocity because it's either plus or minus. I have a negative 30 for VO, and I have 340 minus plus 40 for Vs. And so if I take the ratio of those two multiplied by 1000, I get 1033 hertz. Okay. So if you have any questions about that, please send me an email. Now let's consider the case when the train will eventually pass the car, and we'll ask what is the pitch of the train whistle when it's on the other side. So now it's past the car. So here's the car, and we still have the people inside. And now we have the train, which has somehow become longer. I don't know why. Sorry about that. And it's moving 40 meters per second. And this guy's still moving 30 meters per second. And it's still making some sound of a whistle. Okay? And so the whistle again has pitch of 1000 hertz. And the question is, what pitch is heard by the car passengers? Same question. Okay, it's the same formula. F prime is equal to F times V plus VO, V minus Vs. Now this time, still this guy is the source, this guy is the observer. Okay, now the VO, that's for the observer. It's moving towards the source, so it's going to be positive 30 this time. And Vs, that's this guy. It's moving away from the observer, so it's going to be negative 40 meters per second. So in this case, we have F prime is equal to 1000 hertz. And then we have 340 plus VO, which is positive 30. And then we have 340 minus Vs, which is negative 40. So you plug that in, and in this case you get 374 hertz. Okay, so if you compare the two answers, you see that they're different. In one case, as the train is approaching, the car will hear a pitch that's higher than 1000. As the train moves away, it will hear a pitch that's lower than 1000, and that's perhaps consistent with what you remember with train whistles as trains come towards you and move away from you. If you have any questions about this problem, please give me an email. And now what we'll do is we'll cover stuff that's not on test 3. So this is not on test 3, not on test 3. Okay. And so we're moving ahead to chapter 17. This will be stuff that will be covered on the final exam. So the first thing we'll talk about is temperature. Okay, so we all have some notion of temperature. We feel it every day. Today, on a sort of a spring-like day, we know how to talk about temperature in terms of Fahrenheit or in terms of Celsius. Okay, and so there are ways of measuring temperature. There's one unit that's called kelvins. I'll tell you what that is in a second. There's a unit that you know that's called Celsius, degrees Celsius, and you are also familiar with Fahrenheit, degrees Fahrenheit. Okay, now we will be using mostly Celsius and Kelvin in this course, but it's important to know how to convert to Fahrenheit and to convert into Fahrenheit and to convert from Fahrenheit to the others. And I'll tell you how that goes. Now, the boiling point of water, that's used to define Celsius. So the boiling point of water with a certain standard pressure and temperature, certain pressure is the boiling point is 100 degrees Celsius. And how about freezing of water, the freezing point of water? That is 0 degrees Celsius. So that's what makes Celsius convenient, to have these nice numbers for freezing and boiling of water. Now, there's also an absolute lowest possible temperature, absolute 0. Okay, this is the coldest possible temperature. Now, that value happens to be negative 273.15 degrees Celsius. You might ask, what exactly does it mean to have absolute 0? Well, we will learn that, not in this lecture, but in the lecture after test 3, that temperature has to do with distribution of energy in the molecules of air or in whatever material you're looking at. And so you can think about having sort of an absolute lowest temperature by just basically removing all the excess energy from some system. And when you do that, the gas molecules really stop moving, and you do reach what we consider to be absolute zero, the coldest possible temperature something can get to. There's no notion of an absolute maximum temperature. You essentially can heat something up to as high as you want, but there is something that corresponds with things stop move. When they stop moving, they don't have any excess energy, and that's absolute zero. Okay, if I want to calculate temperature in different units, so suppose I have the temperature, I'll call it capital T. So hopefully that's not confusing. T here in this chapter will be temperature rather than time or period. If I measure it in degrees Fahrenheit, the conversion, suppose I know it in Celsius and I want it in Fahrenheit, it will be the formula: you take 9/5 of the temperature in Celsius and you add 32. Okay? So for example, if we want the freezing point of water in Fahrenheit, we take 9/5 of 0, which is 0, plus 32. So the water freezes at 32 degrees Fahrenheit. Okay? And now if I take the boiling point of water, I take 9/5 of 100. That will be divided by 5 is 20 times 9 is 180 plus 32 is 212. And so we find that water boils at 212 degrees Fahrenheit. Okay? Now, sometimes very often it's good to go the other way. If I want to calculate the temperature in Celsius from the temperature in Fahrenheit, then I have to just invert all this. So I have to subtract 32 from the temperature in Fahrenheit, so bring the 32 to the other side. And then I have to get rid of this 9/5 by multiplying by 5 9ths. Okay. Okay. Now, what about kelvins? So we've talked about Celsius and Fahrenheit. How about kelvins? Well, kelvins is related to Celsius in a very simple way. So kelvins is related to Celsius, and it's very simple. You just add the number 273.15, okay, to the temperature in Celsius. So if you know the temperature in Celsius, you just add the number 273.15 to it. And the reason that works, or the reason why that's useful, is because if you look at absolute zero, it's all cooked up so that absolute zero corresponds with 0 degrees Kelvin. Okay, so if I just add 273.5 to negative 273.5, I get 0. So the temperature sort of degrees Kelvin, 1 degree Kelvin is the same as 1 degree Celsius. The only difference is that it's been shifted so that absolute zero starts at 0. Okay, so 0 degrees Kelvin corresponds, let me just write this, 0 degrees Kelvin corresponds with absolute 0. If I want to convert from kelvins to Celsius, then I just simply take the degrees in Kelvin and you just subtract 273.15. Okay. All right. If you have any questions on temperature, please send me an email. In your homework, you have some questions about. You have a little thermometer which will measure the temperature, so everybody knows what a thermometer is, you know. And there's some marking for, let's say, 0 degrees Celsius, and there's some marking for 100 degrees Celsius. And it actually, what it does is it uses a little, the old-fashioned thermometers that you've probably seen with some red liquid inside. Typically it's red, and it expands as it's heated, this little bulb here, and however high it gets to will give you a measure of the temperature. Okay, so There's a little question in the homework on that. It's not too hard, I think. Okay, now let's talk a little bit about equilibrium, thermal equilibrium. Okay, so if I have two objects, when two objects are in thermal contact, okay, what do I mean by thermal contact? I mean I have two objects that are sort of touching each other. So like my two hands, they're in thermal contact with each other. What's not in thermal contact? If I were to take insulating gloves on my hands, and then they would not be in thermal contact with each other. But if I touch them to each other, then thermal energies, sort of the energy of heat, can be transferred from one object to another. And the statement I'm making is when two objects are in thermal contact, eventually they reach thermal equilibrium. Okay, and have the same temperature. You probably know this already. So the idea is you have let's suppose this pen has been sitting in the refrigerator for a while. It's kind of cold, right? And now I'm going to grab it and hold on to it. Eventually the pen, after a number of minutes, will have the same temperature as my body, okay? And so that's what I'm talking about. There's a thermal equilibrium going on here because I'm in contact with the pen. Now, the next thing I want to talk about is kind of obvious, but at the same time it goes by kind of an interesting name, and I want to just mention it briefly. So if you ever hear of people talking about the laws of thermodynamics, and you know, you'll hear this quite a lot. So it's called the zeroth law of thermodynamics. The reason it has kind of this funny name of zeroth law is actually they started off having the first law and the second law of thermodynamics, but then they realized they kind of needed some a more basic foundation to start off with, so they added a zeroth law later. And it says something pretty straightforward. It says if objects A and let's say A and C are in thermal equilibrium, and we say that objects B and C are in thermal equilibrium. In other words, they have the same temperature. Okay? Then A and B are in thermal equilibrium. I know you're thinking that's kind of straightforward. If A and C are equal, B and C are equal, then A and B are equal too. That's essentially all it's saying here. That if A and C are in thermal contact with each other and they've reached equilibrium, B and C are in contact with each other and reach thermal equilibrium, then A and B are also in thermal equilibrium with each other. Alright, the next thing we'll do is we'll talk about counting particles. Okay, and you've probably seen this already in some chemistry class, probably. We'll talk about Avogadro's constant. Okay, so that's named after Amedeo Avogadro. So we'll talk about 1 mole. So the full name is a mole, M-O-L-E, but the abbreviation is M-O-L. And that corresponds with 6.02 times 10 to the 23 particles, or things. Alright? Now it's convenient to write a constant, N sub A, for Avogadro's constant. Avogadro's constant. and that will be 6.02 times 10 to the 23 inverse moles. Okay? And it's useful because often, the reason Avogadro's constant is useful is because the number of molecules or number of anything microscopic tends to be just enormous. And so we want to work with somewhat more reasonable numbers. So if we have capital N molecules of gas, then we write small n is equal to capital N over Na for the number of moles. So we're just factoring out this number. Okay? And by dividing by this, we'll get units of MOL. So we'll attach this sort of, it's kind of a fake unit, to be honest with you, but it just keeps track of the fact that we're counting moles rather than particles. Okay, now the next thing I want to talk about is reading the periodic table. So in your book you have a periodic table, but you can read it anywhere. Your book has a periodic table. And so if we take a look at nitrogen, so we have nitrogen here. Okay, nitrogen has, you see N for its symbol, 7 for the number of electrons, or you can, number of protons if you like, and 14.0067. Okay, that is what's called the atomic mass. The 7 is what's called the atomic number, and N is the symbol for, we're doing nitrogen here. By the way, your homework due on Sunday has a question about nitrogen, and so that's a convenient example to talk about here. So atomic number 7, and the atomic mass is 14.0067, and this guy is the thing we're focusing on. It's the atomic mass. Okay. So you can view the atomic mass in several ways. It's the mass of the atom in units. It's the mass of the atom, in units of one atomic unit, 1 U, which is about 1.66 times 10 to the negative 27 kilograms. Now, I'm telling you this just for your edification, but we won't really be using it this way. The reason we won't use it this way is because there's a more convenient way of thinking about this atomic mass. Okay? So this atomic mass, the atomic mass number is also the number of grams. So grams, and I should note, not kilograms, because that's kind of an easy mistake to make. The number of grams for 1 mole of atoms. Okay? So, in this case, we said the atomic number, the atomic mass is 14.0067. So, 1 mole of nitrogen atoms has mass of 14.0 grams, okay, or 0.014 kilograms. Now, we will often be talking about gas molecules. So gas molecules, for example, of N2 nitrogen has 2 nitrogen atoms bonded together. And so if we have N2, a gas molecule, then, in fact, your homework question asks about nitrogen N2. So gaseous nitrogen, if you find it, well, by the way, nitrogen gas is the most prevalent element in air, and gaseous nitrogen has composition, molecular composition, N2. So if we want to know how much mass for 1 mole of N2, that's kind of simple because there's 2 atoms per molecule. So 1 mole of N2 molecules has a mass 2 times the number we got before. So 14 was atomic mass. If you want the mass for the molecules of N2, just twice that. So it'll be 28 grams. Or if you want 0.028 kilograms. Okay? So we can calculate the number of moles now in terms. Suppose you were told we have X amount of grams of some material. We can calculate the number of moles quite straightforwardly now. So we can get the number of moles from the mass. Okay, how do we do that? We say, okay, so N is the number of moles, that's number of moles. That will be simply the mass, let's say measured in grams, okay, divided by this thing. What we've been talking about is what's called the molar mass. The molar mass. And that's just the number of grams per mole. Right? So when we said, when we took this number 14.0067, we said that's the number of grams per mole of nitrogen. So this is what's called a molar mass, grams per mole. So let's just do an example. Suppose we were asked, suppose we have 100 grams of nitrogen 2 corresponds with how many moles? Okay, simple example like that. So we can calculate the number of moles by just taking the mass and then dividing by the molar mass. Grams per mole. So 100 divided by 28 is something like 3.57 units of moles. Okay? Alright, if you have a question about this, please send me an email. Otherwise, let's go on to talk about the ideal gas law, which I'm sure you've heard at some point, probably in chemistry again. So let's consider an ideal gas. So what is an ideal gas? An ideal gas is a gas that has no interactions between the molecules. A gas with no interactions between molecules. So the idea is we have some container of gas. The molecules just bounce off the walls. They obviously have to interact with the walls because you have to keep it inside the walls. But the molecules themselves don't really see each other. They just pass through. They're essentially not interacting at all. Okay. Well, the ideal gas is there's no interaction between the molecules. And in that case, we can do some very simple things to describe the ideal gas, whereas a more realistic gas is quite a bit more complicated. So let's give you some parameters. So let's first talk about the pressure. So I'll use the term absolute pressure. We're not talking about gauge pressure, so this is the total pressure, the absolute pressure, P. And we need to have the volume of the container of gas, V. And now for the gases, it's convenient to talk about the temperature in kelvins. So everything we do in temperature for the rest of today's lecture is in kelvins. And so it's important that you remember it's in kelvins only. And we also need to know the number of moles, and that's small n. The ideal gas law is a formula that relates PV and T, and the formula is the following. The ideal gas law is that PV, P times V, is equal to the number of moles times the gas constant, which I'll tell you, times the temperature in kelvins. Okay, so R is what's called the universal gas constant, and the value of R is 8.31 joules per mole per Kelvin. Okay. You can check that the units work out. N has units of moles, that would cancel this. Temperature has units of Kelvin, that would cancel that. And so you were left with units of joules in, okay, maybe it's not obvious, but if you multiply pressure times volume, you'll end up with force times distance. Okay, pressure is force per divided by area, whereas volume is, well, it's volume, so it's meters cubed. So you multiply those together, you get something with units of joules. That was a little complicated, but the units will work out. Okay, this ideal gas law is an example. This is an example of what's called an equation of state. An example of an equation of state. And what is an equation of the state? Just something that relates pressure and volume. It tells you if you squeeze something with a certain pressure, how much volume you'll have, or vice versa. If something has a certain volume, how much pressure does it have? Okay, so notice that for fixed temperature, T, that P times V is equal to a constant. So one way of saying that is P and V are inversely proportional. All right. Actually, historically, this is how people figured out the ideal gas law, sort of piece by piece. They would keep the temperature fixed, and they would measure the pressure as they change the volume, and they'd figure out that as you squeeze the volume by a factor of 2, so it's crushed down to half its volume, the pressure would go up to twice its value. Okay. And so that's pretty much how they figured out how this all works for an ideal gas. You can do the same thing with keeping the volume the same, and you increase the temperature, how the pressure would increase. Okay. By doing these sorts of experiments, you can figure out the relationship between pressure, volume, and temperature. Okay. Now, to wrap up today's lecture, by the way, if you have any questions about the ideal gas law, please send me an email. Let's finish up with an example for the ideal gas law. And the example, let's say an ideal gas has 52.0 moles of gas molecules with a volume of 1.5 meters cubed. By the way, I've been asked this before, so I just want to make sure everybody knows this. That 1 liter, so a liter is basically a cube that's 10 centimeters on each side, or 0.1 meters on a side, and that corresponds with 0.1 meters cubed, and so that's 1 times 10 to the minus 3 meters cubed, or 0.001 meters cubed. We don't need that here, but just want to mention that. The ideal gas, 52 moles of gas molecules with a volume 1.5 cubic meters, and temperature of 20 degrees Celsius. And the question is, what is the pressure? Let's say in atmosphere. Units of atmospheres. Okay? So we'll use the ideal gas law. PV is equal to nRT. Let's see, we need T in Kelvin. So we said the temperature is 20. If I add 273, that will give me the degrees Kelvin. So it's 293. And I'll solve for P. P is equal to nRT over V. Okay, so we said N is 52 moles. R is 8.314 joules per Kelvin per mole. And then we have the temperature is 293 Kelvin. And the volume is 1.50 meters cubed. Okay, multiply these together. You get about 8.45 times 10 to the 4th Pascal. Right. By the way, Pascal has units of, remember that has units of newtons per meter squared. If you're trying to keep track of the units, the moles cancel, the kelvins cancel. We have joules per meters cubed. Okay, but a joule is a newton times a meter. So you have this divided by meters cubed, and so you have newtons per meter squared, and that's the same thing as a Pascal. Okay? Now, but I want to write this in atmospheres, so what do I know? I know 1.01 times 10 to the 5th Pascal is equal to 1 atmosphere. So 1 Pascal is equal to 1 divided by 1.01 times 10 to the 5th, times 10 to the 5th atmosphere. Okay, so that was what we'll plug in there. We'll make a replacement. 1.01 times 10 to the 1 divided by 1.01 times 10 to the 5th. So that will give me about 0.836 atmospheres. Right. Okay, if you have any questions about this, any of the lecture, please send me an email. I should be able to respond pretty quickly. Otherwise, I'll see you guys on Monday, and on Monday we will do a full review for test 3. See you then.